We're here to talk about robots in space, an absolutely cool topic that offers so much depth, particularly in AI, autonomous driving, software developments, all of that. And no one better to help us lead this conversation than Vandi Verma, who is the Chief Engineer, Robotics Operations at NASA's Jet Propulsion Lab, also a private pilot. That is known as JPL, by the way. Hi, Vandi. How are you?
Hi, great. Thanks for having me. I'm looking forward to this.
Absolutely. We also are joined now by Raewyn Duvall, who is with Carnegie Mellon University Robotics Institute, also formerly with NASA. Hi, Raewyn.
Hi, how are you doing today?
I'm great. Thank you. I'm also here with Nikolai Stefanov. Nikolai, tell me what you do at Carnegie Mellon University.
Hi, I just graduated. I was a physics and computer science major. Just graduated a couple weeks ago.
So, Vandi, let me start with you by asking you, tell me about your journey and how you ended up at JPL doing what you're doing today, because it had a significant start with your time at CMU.
Yeah, absolutely. So I started at Carnegie Mellon. I actually always, wasn't even sure I wanted to do a PhD. And I took a class on mobile robot programming. Actually, Ila Nurbaksh was teaching the class, and we would learn the theory during the day. And we would program the robots, but it was so much fun that in the evenings, we'd be spending all night running our robots around at that time, Wien Hall. And I really enjoyed that tremendously. And there was a Mars technology program, and it funded us to do robotics in the field. I actually started with the Antarctic Meteorite Search project even before I started, the summer before I started my doctorate. And it was fantastic to work with actual NASA scientists and see what it was that we could do with our robots. And I think after that, I was just sad, and I never looked back and have continued to work on, planetary robotics.
Vandi, living proof of the power of internships. And Raewyn, a similar story for you. Tell me a little bit about your path to where you are now.
Yeah, so I did an internship at NASA in software for ground support for SLS back in the day. And when it was still on the Journey to Mars program and everything. And I got that during undergrad. And I guess they liked me enough that they heard that I liked robots once. And when they weren't my software group wasn't able to hire me at the time, they sent my resume to the robotics department at Kennedy Space Center. And so they brought me on with not much robotics experience myself yet. And so right out of undergrad, I was introduced to planetary robotics and on-site resource utilization for robotics, ISRU in situ. And it fascinated me that you could send robots up to prep everything for astronauts getting there. And it was the first step really for getting people up there to the moon and to Mars.
Nikolai, tell me a little bit about how you found out about IRIS. And for people who aren't familiar, what the project was.
Yeah, so I joined CMU in 2019, came in as an undergrad freshman halfway through my first year. So maybe about December time, I had to go print an English assignment or something like that. There's this poster above the printer saying, there's never a second chance to be first, with a QR code, sign up. It was about IRIS. It was this shoebox, IRIS's shoebox on bottle caps. Was the first university developed rover to go into outer space. Back then, it was like all about the lunar surface and stuff like that, studying the terra mechanics of it. But incredibly light, incredibly small, smaller than really anything, any other type of rover. So it was incredibly interesting, especially because we got to open up space to so many different, students from all over the university, from who are in turn are from all over the world. So it was really cool being a part of that whole experience. And then once I joined, I really just couldn't leave. So being a part of it for like 4 years was just incredible.
Vandi, I'm coming back to you here in just a second, but I do have to talk to Raewyn first about this. So IRIS, unique and precedent setting in so many ways, and ultimately did not meet its original mission objectives, but absolutely accomplished so much in the space. Walk me through that.
So yeah, we unfortunately we didn't reach the surface of the moon, so we couldn't do our tech demonstration of driving on the moon specifically. And that was our main purpose, especially because Iris was made so that it couldn't actually drive in Earth gravity. So that was sort of a big step that it was hoping to accomplish. But at the end of the day, Astrobotic turned us on when Astrobotic had their fuel leak, and they knew early, and they were really transparent about it. And so they worked with the payloads to turn us on in space, which was not something we were expecting in any way, shape, or form. And so but it gave us a little bit longer mission time in the end, because we were supposed to just be on battery power. Suddenly we had lander power for the entire thing. And so we were able to check out almost all of our systems. We were able to drive in space and be the fastest rover ever. And sorry, Vandi, we're going to beat y'all on that one. But yeah, it was incredible. So we got to drive the wheels, and we got to check out all of our communication systems, our wired communications, and all of our sensors and things like that, and see that we were getting all of that data, which was absolutely wonderful. And the two things that we weren't allowed to test, which was Wi-Fi for FCC reasons, and our cameras, because they were covered to mitigate getting dust during landing, we were able to check out prior to launch. And theoretically, they should have worked better on the moon, because they were designed for, distance for Wi-Fi and the moon lighting and everything. So that was great, because we're able to do almost all of our proof of concept, except for, as Nikolai said, some of the science we were hoping to do was terra mechanics, but otherwise our proof of technology we're able to write about and really say that it succeeded and that it could be viable. So
space exploration has been predicated on human beings overcoming tremendous challenges, things that happen unexpectedly. And Iris and the way that the team of, maybe it was 30 of you, if I read that correctly, came together in the moment in Florida in that house to execute an entirely new mission set is applicable to the work that Vandi is doing. And Vandi, I know you picked up on this when they were talking about Iris. Iris was never designed to drive on Earth's gravity. And so much that you're doing in what I would describe as the larger rover space, if you will, is running simulations and using artificial intelligence and creating as best you can mechanisms to see success when NASA machinery touches down on the Martian surface. Walk me through how you see all of this sort of coming together in the framework of the students, interns, now NASA employees, all working together for the common good here.
Yeah, and it was so fantastic. I followed the Iris rover because I visited it when I was at CMU and got to hold it. So it's so great to see, because I think that what you learn through actually deploying, trying to get a robotic system to work is extremely valuable. And that's something I think I started doing at CMU. And there's a lot of places doing it, but in the beginning, there were very few, and CMU was one of them. I thought that's a really valuable lesson. And it's an extension of that in some ways, like you said, in a much bigger form that we do at NASA. But it's not actually that different fundamentally from what you start learning at those early stages. One of the challenges we face, and I worked on MER. In fact, I was at CMU. I remember watching the MER landing from the student lounge. Never thought I would actually get to work on those rovers, because it was supposed to last 90 days. And I graduated and they were still driving, because, lasted, 14 years opportunity, and got to work on both Spirit and Opportunity. And seeing them on the surface of Mars, I then got to take those lessons learned into Curiosity. And I worked on a lot of the software, like you said, simulation and testing for Curiosity, and then got to do it for Perseverance. And so it's these iterations when we're on the surface, you sort of see it is a different planet. It looks so much like Earth, but the gravity is different. The atmosphere is different. Human beings couldn't actually just survive there. So you start to realize we are in a very different place, and we need to build our vehicles in order to be able to anticipate situations in a place nobody's ever seen. that's the part that gets really interesting, is not building it so it you limit yourself too much because you're sort of anticipating too many of the risks, but also thinking of what if, all the what ifs, and designing the system so it can survive despite that. And with perseverance, for example, when you're landing, we rarely ever land in exactly the center of the landing ellipse, because landing on Mars is so challenging. There's a lot of uncertainty. So for robotics, that's one thing that's really interesting. You have no idea where you're going to be put down. And then you start your mission from there, and it has to be from wherever you're put down. So that's one of the really interesting aspects.
Is there a risk of over preparing? Because we are limited. You haven't set foot on Mars. We haven't actually seen it. We have some pretty good pictures now, thanks to the work that everyone is doing. But the reality is we're learning as we go. So how do you approach that using artificial intelligence and some of the other technological tools available to you when you can't actually physically truly test the atmosphere until you're there for the first time?
That's the part. I really love that part. And every new place you go is unique, because that is what makes planetary robotics really different from a lot of the terrestrial robotics. Often in terrestrial robotics, we do have map, we have a lot of knowledge of the area. And planetary robotics, you rarely do. And as we are going further out into the solar system, it's going to be not even anything like Earth, some of the planetary bodies like Moon and Mars are. So in some ways, you have to draw the balance between the safety checks being such that you constrain the vehicle so much that it doesn't do realize its potential. So there is that trade-off. So I think I think what you were saying is, can you limit the vehicle so much because you are being too conservative? And absolutely. And that is the fine line, you're right, to say, what is this robot capable of? And can I maximize that without destroying it? Because I think as Nikolai was saying, you don't get that second chance. And so you have to take that into consideration.
I do want to ask you, Nikolai, to take me inside the house. Take me into is there a story, one particular story that you like to tell when people ask you what it was like, that sort of encapsulates what it is you're talking about here, or just a funny sort of moment?
Over the course of a year, we were doing mission simulations nearly every weekend, and that would be 4 to 8 hours every Sunday when, people had classes, they had homework assignments, they had exams the next week. But, we'd get up at 10 a.m. or earlier to set up the mission simulations, and we just practice our communications. In those moments, we'd really kind of get to bond. And like Raewyn sort of, I think, touched on, we had the mission changed a lot. We didn't get to the lunar surface, but I think given all the practice we had, and we just onboarded some new people as well, expecting maybe a month of transit to train them as well, before ultimately going to the lunar surface. We didn't have that, but still everybody adapted. I think in that small house in Florida, we just kind of, mission was now. Pizza boxes were stacked to the ceiling in the kitchen. We're all trying to figure out, we had media and stuff coming out, mission was a failure, wasn't going to make it to the moon, it all happened. But, I think seeing the team, it wasn't everything we've done up to this point isn't going to work or matter. It was, what more can we do? We still have this opportunity to maybe get some valuable information out of it. And, the beach was a couple blocks away. Instead of going down there, we just spent all-nighters. We were trying to figure out how exactly we could transition our mission to make it applicable to this new scenario. And I think that was just incredible to see, incredible to be a part of.
I have to come to Raewyn first before I go to Vandi, because, you recall Raewyn, Vandi describing her first experience with robots and how she spent all night. And this is exactly what Nikolai is saying. And I'm assuming it's the same thing for you. It is not work when it's what you want to spend all of your time doing.
100%. I think I come from a slightly different vantage point where I worked before coming back to school. So I had dogs that I needed to take care of. But other than that, 100%, I mean, I would come home, feed the dogs, go back to the lab a lot of times when prepping. But I think that one of the things that Vandi touched on and that Nikolai really pushed for and like led for with the team, like he said, it's all about the team coming together. Because we were a private one here, we were able to have almost like nationalities from across the world. We had some of the first Singapore students on a space mission like this. That was one of the biggest things, is that we did have that international group, and it wasn't work. And it was really fantastic seeing that team working overnight, like Nikolai said, coming up with a whole new operation. That house was meant for 12. So we kind of packed in like sardines. They were taking shifts on like naps up in the beds, things like that, pizza boxes stacked. But Nikolai really, as the mission started and Connor and I are, we need to start sending commands unexpectedly soon, and trying to set up a little mini mission control. Nikolai took charge, got the team together, and they came up with, within the period of a couple of weeks, Vandi can probably talk about how many years it goes into just planning the mission usually. And within like 12 days, less than 2 weeks, the Nikolai and the rest of the team came up with and modeled and did everything they could to do a initial proof of concept for an entire new operation if we were able to be ejected from the lander. And it was absolutely amazing what these students did in 12 days, came up with all the presentations, and we fought hard and long for it. But at the end of the day, we couldn't be random space debris. But it was amazing what they did with that.
Vandi, you are sort of the end user of a powerful team and excellent technology. What is the value of having a team with broad perspectives as you tackle some of the biggest challenges in space?
It's such a crucial part to be, to have the diversity and inclusion. And it's actually one of our strategic mottos at JPL, and very much so. Partly, we're doing something that has never been done before, typically. A mission, that's generally the sorts of problems we tackle. They're one of a kind. And you need to have ways of thinking that are diverse. And people like, Nikolai and Raewyn pointed out, right? Like they bring their whole selves to these problems. When you're part of these teams, right? You're working, you're literally, you have to feel, and so they should be able to bring all of themselves, because that is what being part of a team is. At the same time, usually people from diverse backgrounds have come to this through very different paths. And that results in a different way of approaching the problem and forcing us to think. And you don't get stuck in plateau. And I think that's absolutely crucial. We're always sort of not trying, we're always trying to think of, like, if you come to a bottleneck, what is the many different ways in which we could tackle this? We do brainstorming sessions a lot when we're doing, because you don't want to just take the first good idea and engineer the heck out of it. You actually want to start out with a lot of great ideas and then pick it, because actually you can make that mistake. So I think the diversity helps a lot with that. And the diversity can come in all, like you said, it's across the spectrum, having teams that have different levels of experience, different genders, different nationalities, all of this, they come from different ways of having approached problems, just because that tends to be correlated. And I think that's very crucial.
I am sitting among a group of people who hold the distinction of doing something that the vast majority of the world will never get to do. So, and that is send something that they have had a hand in to space to serve a scientific research purpose. Vandi, I have to ask you, over the time, because you've been doing this for a while, so I do want to have a little bit of fun with this. You've gotten to know the Martian surface in a way that blows my mind. What have you learned about piloting rovers on Mars?
Right. It is kind of strange to think that it's been a long time. I've been doing this, since 2008, pretty much every day. And so what's interesting about it is you can both go in, and it's so familiar because you've seen different parts of the planet through actually, 4 rovers and a helicopter, very different views. you can kind of get a sense of it being, it's a lot like Mars is a lot like Earth. They're rocks. It's a lot dustier, but still, we name things on Mars correlated with places on Earth because they are those similarities. And I think sometimes you step away, and when Mars is visible in the night sky and you see it in the sky, it is kind of like, it is really far away. And it's sort of a realization that, that it is, that we do, and we have a robot up there. It's interesting because there is a sense of, it's like flying airplanes. We were talking about that, where it is both that you need to focus on the instruments and your skills and what you do, but at the same time, there is an intuition and an art that is part of the driving and navigating. Knowing what terrain will be accessible and easy. You can look at the stereo images, you can measure the rocks, you can do the simulation to see how the rover's software will respond and be able to tackle it. At the same time, if you've done it a lot of times, you automatically know what paths are navigable. There's also the challenging part that we are actually going there to do science. That is generally the main focus of all of the planetary science robotics that I've worked on. And you need to correlate, what are the scientists interested in? Is my robotic arm going to be able to access this? Can we get that science measurement? So you're both looking at getting there, but also can the robot, with what it's capable of, because it has its limitations, it might have a 5 degree of freedom arm, which cannot access arbitrary positions. Can it get to what they're interested in, or should I do this differently? So that becomes both the challenge of kind of putting yourself from the perspective of the robot, but also using the broader human intuition you have to guide the robot. So you're essentially both the robot and yourself. I mean, it's a little bit out there, but it is interesting how that works, using both of those, capabilities.
Human beings are good at both establishing patterns, for better or worse, and also coming up with solutions and uses for technology that were not intended originally. I think Raewyn and Nikolai have talked about how quickly they came up with new mission sets to try to gather as much data as they had. But Vandi, can you walk me through some examples of technology? I mean, you mentioned this, freedom of movement with the arm and measurements that you could or could not take. Were there other examples where technology that was present on your rovers was able to capture data in an unintended way that was interesting to you, something you weren't expecting? Or is it so polished at that point, because of your simulations and things that you've run, that there are very few variables left for you?
We absolutely use the rover in ways that we could not have imagined before we landed, all of the time. There are so many examples. And that is really fun because now you really know it, so you know what you can do. So some examples. The images, if you have ever seen a picture of all of Curiosity, or if you've seen a picture that had both the Perseverance rover and the Ingenuity helicopter in it, there's only one picture that has, the picture in it. We call it a selfie, which you take the robotic arm and you take a picture with it. That's not really a scientific purpose, but, we wanted to have a picture. It takes, we had to take over 50 images, stitch them together because the camera that we took it with, the Watson camera, which is at the end of the robotic arm, is meant to do close-up microscopic image look at rocks, not meant to take a big picture of the rover. So this is just a fun example of how we used it to document the rover and helicopter by taking the arm. It has to do flips, shoulder flips, and wrist flips, and it takes an hour of arm motion. And if you haven't had a chance to look at it, it's really fun to see what it takes to take that picture. So that's one example. Another is, we landed with Curiosity, and we had, as Raewyn was pointing out, right? Like, it takes a lot of planning to make sure they're irrespective of what Mars and the planetary body is going to throw at you, you can get the science you want. And yet, we landed, and the first sight we had after we sampled that rock nest with Curiosity, the scientists had this instrument called SAM, Sample Analysis on Mars. It was literally like taking an entire laboratory and they had put it on inside the rover, and we were going to deposit samples on it. Like everything on the rover, the instruments also have a lot of knobs. You can adjust these to optimize the experiment. And they wanted to be able to do that a lot. So they basically said the design was you sample, you drill into the surface, get a sample, drop it into the instrument, you clean it out, go drive, get the next one. Well, they were like, we're not ready to get rid of this. We want to hold on to the sample. We want to keep experimenting with dropping it. We had to figure out a way to squirrel it away in the robotic arm hardware in a place that wouldn't be dangerous to the hardware and wouldn't spill, and then drive and deposit. And we had to do this after we had landed on Mars. And we were able to do that. And we did that for years. It drove around because they continued to want to do that. So this is another example of something, even after you have, hundreds of scientists and engineers work on something, the planetary body will surprise you. And then you will use your knowledge of what the robot's capable of to adapt to it. And I can keep giving examples of this. We're actually doing this with Perseverance as well. The space computers that you need for NASA qualifications for radiation hardening are usually really slow. I mean, your cell phone has more computing than the Mars rover. But Ingenuity was a technology demonstration and was allowed to break some of these rules because it could take more risk. So it did use cell phone parts. And so once we landed, we wanted to localize. So as the rover's driving, we do autonomous navigation. But because there's no GPS on Mars, the rover kind of slowly loses track of where it is. And we have ways to keep it safe with our uncertainty increase so that's not going to drift off into a crater or onto a sand trap. But that, as we're driving further, as autonomous navigation is getting better, that error is becoming really large. So we now have a new thing we're actually in the process of deploying on Mars, where we use Ingenuity's computer to do computing for the rover. So we ship off the computing, and it tells us where we're on Mars, and then the rover will update its pose and be able to drive even further. So these are just examples of us using what the capabilities we have to do more than what we had initially, planned for.
I'm glad that you continued with that example because it was actually my favorite when you mentioned something as simple as a phone and the compute power that is available up there. That opened my mind in a way I was not anticipating. Nikolai, what do you want to do with both this experience that you've had as well as the education moving forward when you hear even just about all of the developments that have already happened in such a short amount of time?
The opportunity to just have something sending something up in space, whether it be a CubeSat or whatnot, our future rovers. It's a different feeling that's really hard to capture, I guess, and hard to put into words. But I like that aspect. I'm looking forward to that, I guess.
As a physics major, can artificial intelligence work in tandem with you to help solve some of the challenges and the high-level computations that are required for you to be successful in your endeavors?
I know one specifically is just sort of artificial intelligence for data at the Large Hadron Collider. It receives so much data. Putting that through an artificial intelligence to be able to tell you when, let's say, a Higgs boson particle might appear. So you actually save that data as opposed to like other data. Or if we're focusing more on space too, I mean, in order to get to the far side of the moon, what's really nice about it is that it's radio dead. What makes it really hard to command something when it's in a radio dead space. So maybe if you have a satellite that passes over in orbit, maybe 100 minutes or so like that, you can only command it, let's say, every so often. If you want to sort of keep moving along, let's say you're trying to maintain a path of constant daylight, then you kind of need the rover to drive itself. So that's artificial intelligence there is vital.
Raewyn, in the context of this conversation, what are you excited about? What do you hope to see with artificial intelligence partnering with space exploration?
I think artificial intelligence is amazing for what we can do far away, I guess. If we, are going out of the system, out of communications range, artificial intelligence will obviously help a lot with that in so many ways, being able to be autonomous. And so while I think AI brings so much to the table, especially on those farther away things where you can't really realistically have a human in the loop making those higher level decisions, even if it's autonomy driving those individual waypoints, that's still, human ingenuity in a lot of ways, right? That's humans planning. But I think that it's something that I love what it brings to the table as an addition to these missions. But I would be hesitant to say from a personal level that it is a controversial view for sure, but that I would fully want a mission to be, fully autonomous or fully AI driven.
I don't think it's as controversial as a take, just from my perspective in speaking to other academics affiliated with CMU. I'll come back around to all of you to ask for some closing thoughts here. But Vandi, I want to talk to you about what needs to happen in the field of robotics and AI to help take what we are doing in space to the next level.
That's a great question. I really think that we're at this juncture where we've done enough that we know that we're capable of doing this. And I think we can make bigger leaps. I think we need to there are some of the, Nicholas talking about the physics of space as such that there are challenges just with getting to really far away planetary bodies. And we cannot send a mission that takes us, 6+ years to get there and not have taken advantage of everything that we could possibly do at the time we're there. We're still talking to Voyager, and actually we just updated the software on it, right? And if you look back at it, it's both a marvel that we could do this, and yet you're like, oh my gosh, it's so crazy. Look at the memory it has and how they had to do this. And that's what's going to happen just because of time as things are going. So we have to use the latest technology. And I'm a big fan of using the AI. In fact, we have some of it on board to do the science. There are things that humans are really good at, but there are things that AI, utilizing the information that the robot has at that moment that we didn't have at the time we sent the command, that it can do, is fascinating. And we use this as a way, as we're driving long distances, we take a picture, wide angle image, and we're like, what is it that with my laser, we have a laser that we shoot that creates a plasma, and we take a telescopic image of it. You can't do that with the entire scene. So which one should I pick to do that on? That's something, is an example. And you base it on what scientists think are important, but now you're basing it on this very approximate information. So this is one example. But in terms of the technology going forward, we actually did a report on talking about what NASA should invest in terms of technology going forward. And we actually put a picture of Iris in it, actually, because it's the example of both. We need to go small scale, and we also need to look at the whole spectrum, driving really long distances, going, 1,000 kilometers on the moon in the South Pole Aitken Basin, plus we need to go to other planetary bodies. So I think we need to have more ambitious missions. We need to have take ways in which we can do science, really realize the full potential, and utilize what we have learned so that we maximize the success. So, things like there are things we know that we can test, and we are comfortable with the uncertainty. We do need some form of the determinism, but at the same time, we can maximize the probability based on what we know. So I think that those are things that I would really like to see us do.
The future is bright. And as Raewyn has talked about, both the collaboration between humans and then using the right tool, which is what I'm sort of distilling down from this conversation. Nikolai, do you have any closing thoughts for us as we wrap this up?
I think the biggest thing, and touching a bit on what Vandi was just saying, more ambitious missions are always very nice to see. And it's also just, we've talked a lot about diversity and everything like that. And it feels like we're getting to the stage right now where, we have other countries sending rovers to the moon for the first time. We're having that diversity sort of in this new sort of space age. And we've seen what that can do on a small scale with a team, how it transformed our operations and whatnot. It's just going to be very exciting to see what that's going to do for the future space exploration.
Raewyn, closing thoughts?
Yeah, I think, as Vandi said, using the most recent technology, I think one thing to touch on, again, kind of with the inspiring the world and everything like that, it's an interesting take. I think one thing that moving forward, being able to do faster turnover as it's opening up to these private industries, faster turnover of these missions is really important because, you do have to use the latest technology for a 6-month or 6-year getting to your destination or longer. And even IRIS, there were so many years before we actually were able to do our mission that Mars 2020 went through, and Ingenuity happened. Curiosity and Ingenuity happened. And Ingenuity was basically IRIS, but in helicopter form in a lot of ways. And we worked with the Ingenuity software team to do IRIS software. But by the time we were launching, Ingenuity showed that some certain processors, the newest technology, would work on Mars, and like a Snapdragon could be used even in these more radiative places, but could still be reliable. And, IRIS, though, by the time we launch, our technology is already old in a lot of ways. And so, space is getting to finally is that higher turnover rate of sending up missions. And I think that it's amazing to think that these missions are inspiring the current world, and they are finally the ones getting to see them through, versus the longer term, that's old technology, why are we still using it questions. So
Vandi, closing thoughts.
I really have to say, like, when you see things like, the Nikolai and Raewyn and others, like students and undergrads included at university are sending things into space. Just imagine what we're going to be able to do in the future, right? Like, I'm really excited for the future because we are getting more possibilities with students experimenting with things really early. And that's the part that I felt was something that really set me up well, was from CMU. I was experimenting with putting theory I learned in classes on the robots. And now they're taking it another level and putting it into space. So I'm very excited for the future.
Robots in space. What an incredible topic. Thank you so much, everyone, for your time. You've been listening to Does Compute, the podcast that examines how computer science is building useful stuff that works. I'm Steph Stricklen.